Okay, hello everybody. Welcome to this session. My name is William Copeland. I'm one of the organizers or co-leads of this session, Navigating the Changing Arctic, Innovations for Sustainable Maritime Development. The other co-lead is Benjamin Strong. He's sat there. He's representing the US group of the Arctic Council Working Group, Emergency Prevention, Preparedness and Response. We have other members of the committee here too. We have Ed Blockley, who's from the Met Office, head of the Polar Climate Group. Do I see Martin Schedsma here? He is a representative from COSAT. We also have Malin Johansen, she's not here today. And Penny Wagner, she is the head of operations at the Norwegian Ice Service. So what are we doing here today? We're here to talk about what's happening in the Arctic in terms of maritime activity. We know that climate change is having a large effect on the ice. We know that these shoulder seasons are extending, and this is opening opportunities, but it's also opening quite big challenges. So we're going to be looking into scientific advancements and limitations. We're going to be looking at gaps in policy and also data, observational gaps. And we're also going to be looking at implementation challenges that we have for bringing in products and also policy for both operations and for end users. Now, I'm going to do a bit of practical information. We don't have much time, so I want to get going as quick as possible. Today, we have 6 speakers, but we've split the whole session into 3 parts. So 1 today, 2 tomorrow. Today, the 6 speakers will have around 8 to 10 minutes to present. We're hoping that there's enough time for questions, about 2 minutes, but if they go over time, I'm afraid there is no question opportunity. Towards the end, we will try and have a panel discussion in the time remaining where I will propose a question, and then you'll get the chance to ask questions if you didn't get the chance at the end of the presentations. All good? So I want to start straight away so that we have time for questions. I'm going to start with Malte Müller. He is a researcher at the Department for Research and Development at the Meteorological Institute and also a professor at the University of Oslo. And he's going to be presenting on Arctic shipping trends during hazardous weather and sea ice conditions. Thank you, Malte.
Yes, good afternoon. And thank you very much for this introduction, William. Just have to check the... Okay. Yes, thank you for the opportunity for this introductory presentation for this session today. This work is a result of an interdisciplinary social natural science collaboration we had over recent years. They were funded from the Fram Center projects Sudaco and Prismas. And I worked together with my collaborators, Maike Knoll-Kaufmann from the University of Tromsø, and Jelmer Juring and Sigurd Palerm from the Norwegian Meteorological Institute. So the presentation is about weather and sea ice hazardous conditions in the Arctic. And if you think about yesterday, that was a perfect example of a hazardous weather condition. And if you followed the news, or some, I think, experienced it even yourself, the whole airspace of northern Norway was closed, and also the shipping along the Norwegian west coast was quite reduced. And one of the results of that kind of measures were that there was no major incident happened. And in that sense, the weather information services and the decision makers and the regulations work quite well together, you could say. And this is in principle what we are working about as well, but just more northward for the central Arctic and also including sea ice. We would like to optimize this regulative framework, the sea ice and weather information forecasting systems, and the operational decision making in order to minimize the risks. So I will start with some more general slides to introduce to you to the topic. So this is about the sea ice loss. I guess a lot of people have seen this already. This is how sea ice changed over the past 60, 70 years, and how it will very likely will change over the next century. So we will have more and more opportunities to for like better accessibility to the already established sea ice routes, the Northwest Passage, and the Northern Sea Route, but there will also more and more be the Transpolar Sea Route be available. And one of the reasons why this is interesting is that, of course, these kind of sea routes are shorter compared to going to through the Suez Canal. Sorry, that was the wrong button. Compared going to the Suez Canal, and also what we see in the last month is that also going in this area can have also other problems. So the Northern Sea Route and also other sea routes through the Arctic will be more and more popular, also in terms of sea ice loss, but also maybe in terms of security standards. So what we already see, there's actually a typo on the slide. So this is not about the Northwest Passage, it's about the Northern Sea Route. It's from the PAIM shipping assessment in 2019, and they looked at the trends from 2013 to 2019. You can already see in the Northern Sea Route that the number of unique ships increased by 44%, and that the distance sail roughly doubled over these few years. So it's quite an increase already. But it's not only the transpolar shipping which is important in that context. It's also like the shipping from, like the destination shipping from the Russian Arctic to transport the oil and the gas which is extracted in that region. So in our study, we wanted to look into these increased activities, but we also wanted to connect them to the weather and sea ice forecasting infrastructure we have, so the services we can provide potentially. And in addition, we want to look into the regulative framework, and in this case, it's the Polar Code. So we were doing this by using the Arctic ship traffic data set. So it's a database which is continually developing over time, and it's hosted by PAIM. So the presentation right after me will present more details about that. And we were using this data. It's quite a huge amount of data. It gives the ship positions of all Arctic, of all ships of a certain size in the Arctic, and we combined them with an atmospheric reanalysis. So like a reanalysis is a product where you have a time series basically also of the weather in the past. So for each ship location basically in the Arctic, which we can identify from this kind of data set, here we can relate it to the weather it was exposed to, and then we can do the same with the sea ice. So we also added a sea ice satellite retrieval, and then we can see which ships are exposed to sea ice conditions. And that's something we did for this time frame from 2013 to 2022. So very generally, we analyzed the trends. So from this ASTD database, we can have sectorial information. So we know for each ship which sector from which sector it is. And that's a result here. So the colors basically are the different sectors. The brown color here is, for example, from fishing. And then this is the annual mean for all ships without the fishing sector. And this is all together, like all sectors combined. And what we find is that there's about a 12% increase per year of shipping days in the Arctic over the past 10 years if you exclude fishing, and about 7% when you include the fishing sector. So that's quite a lot. So if we specifically focus into the Northern Sea Route, the trends are even stronger. So the same graph here, but for the Northern Sea Route, you see trends of 9 to 15% per year. If you look into the transits, so the individual ships which transit the whole Arctic via the Northern Sea Route, you don't see the same trends. And that also, I showed it already earlier, has to do something that this kind of shipping is mostly, or like the increase is mostly related to the oil and gas explorations in the Russian Arctic. Sorry. So we looked a bit more into detail into this, and like for the summer shipping right in the beginning of the record, and then more later in the record for the winter shipping, and you can see that here in the summer there was not a lot of shipping going on in the Barents Sea and the Current Sea, even in the summertime. But here later, after the establishment of these big oil and gas projects in the Russian Arctic, you have a lot of shipping, although it is winter and although there's quite some sea ice. So that was one of the causes. We want to go a bit deeper into the data and actually compare to which ships are actually in the sea ice and what is actually a hazardous condition. And for that, we used the Polar Code. So the Polar Code regulates quite a lot of things, but specifically towards weather and sea ice, there's a ship classification, and there's one about sea ice. So there's a category A, B, and C classification for the ship class, for the sea ice class, and in addition to this, there's a polar surface temperature, which has to be below -20 degrees. So, but it can be also lower. And this is kind of connected in the Polar Code to the Polar Water Operational Manual. So this is kind of a manual on each ship, which needs to have procedures to avoid hazardous sea ice and temperature conditions. And one of the general recommendations how to avoid this is the use of climatologies. There's a mentioning of forecast information in the Polar Code, but the most specific statements are about climatologies in this. So the questions we had then is that how much ships are actually opposed to those hazardous conditions, and how could sea ice forecast information become more relevant in this context, and are there actually other relevant hazardous conditions which could be taken up in the Polar Water Operational Manual. So first we analyzed all the ships which are in the sea ice larger than 80%, so it's in closed sea ice conditions. You can see this here for one specific year. This is all the dots here from the different sectors, and you see that almost all of the traffic in sea ice happens in the Northern Sea route. And if you look at the time series, you can also see that there's quite some increase over time for the shipping days. So this is basically the amount of time ships are exposed to sea ice. And you can see that when you are looking at the beginning of this time series, at the peak here, which is in winter, it's about 300 days. In the last years was already about 1,000 days. So it's roughly a tripling of the amount of time ships are actually exposed to heavy sea ice conditions, or to closed sea ice conditions. So one case study here to express a bit the concern about climatologies. So this is now a climatology here this is a part of the Northern Sea route. This is the East Siberian Sea, and this is maybe a prominent road here you can think about where ships can go. This is the sea ice concentration in October in an average from a climatology. And you can find that for an ICE2 classified ship, so this should not be ARC2, it should be ICE2 actually. So for an ICE2 classified ship, this is category C and the Polar Code, a ship would be allowed to go still there in October according to the regulations. But it would not be allowed if the sea ice concentration is above 10%. So what happened in October 2021 is that there was an early freeze-up, so it was quite an anomaly compared to the climatology. And in these conditions, an ICE2 categorized ship would not be allowed anymore to cross the East Siberian Sea. But as you already see, there's this ship which is called Golden Suk, which is an ICE2 categorized ship. It's just about entering this area, although it would not be, although it would be restricted. So this is the same figure again, and this is on the right side. You see it just a week later. So the whole East Siberian Sea is covered by ice. So it was a very fast freeze-up of this area. And you can also see that this Golden Suk and Nordic Uliak here are positioned at one point. And it was actually that they were drifting there for 10 days before they could be escorted out of the sea ice. And it was 10 more ships which were in trouble as well. So there was only one icebreaker close by, and where all of them were then escorted out from this area. So again, according to a climatology, you could not expect this kind of situation, But the question is then if a forecast information could be good enough for this. So we looked into one forecasting system. It's a 10-day forecast here from the Topaz 4. It's part of the Copernicus forecasting systems. So this is the forecast information we would have had 10 days before Golden Souk was at this point. And actually Golden Souk was departing from Murmansk on the 18th of October. So then this forecast was already 6 days old. So like if you think about route planning at this stage, there would be clearly a chance that this ship should not have gone into this area. So this was about sea ice forecasts. But then we also had the question that additional to this very low temperature requirement and the sea ice hazardous conditions, are there actually other hazardous conditions which are missing? So we analyzed the data set from a perspective from sea spray icing, which is a well-known Arctic threat for ships. And we analyzed it in the same way, and what we found is that it's mostly fishing vessels which are exposed to sea spray icing conditions. So these are here dots for like extreme heavy and moderate sea spray icing in 2021. And you see it mostly happens in the Barents Sea and in the Bering Sea. And again, to stress the importance of a forecast versus a climatology, I would also like to show you like a case study. So this is from the Onega case in 2020. So it was a fishing vessel which sank in the East Barents Sea. So that was at this location here. Here you see all the dots for the specific area. So you see in this area specifically, there was moderate to heavy sea spray icing. And these were the last tracks basically from the ship. So the red dots are the last 3 days of its voyage before it sank. And if you look at forecasting system data, we can see also that here a forecasting system would have quite good indicated that first, before, like in a relatively long period, the ship was under moderate sea spray icing, so it might have accumulated already quite some ice over that time. And then the weather situation changed to more severe conditions, and that was already forecasted here several days before the ship sank here in the end of the record. So again here, it would be quite important information for the ship, possibly. So if we think now about limitations of the Polar Code, we can first look into the WWF report from 2022. It's quite a comprehensive report which went through the whole Polar Code and looked at limitations and gaps in its implementation. And specifically connected to weather and sea ice forecasting, they write, it's neither strong enough nor clear enough about the tools and data needed for safe navigation in polar waters. And that's something we clearly underline also with our study. And we go also one step further, and we have a suggestion that there should be a better alignment with the weather and sea ice forecasting infrastructure, which already is in place. So, and this is the Worldwide Met-Ocean Information and Warning System. So this is a system hosted by WMO and by IMO, and it basically divides the global ocean into about more than 20 areas. So the Arctic is divided into 5 areas, where 2 of them are coordinated by Russia, 2 of them by Canada, and 1 of them by Norway. And for these areas, each of the countries give specific warning information via marine tailored systems to ships. But it's not necessarily connected to the Polar Code yet, and not to Arctic conditions. So but it's already in the SOLAS convention. And it says that all ships which are larger than 300 gigatons, and for all passenger vessels, they have to carry such a NAVTEX recorder, so they already get this information. So there would already be quite a framework to go further and to connect this kind of service with the Polar Code or with the regulative framework. And this brings me also to my last slide. So what we showed is that Arctic shipping increased over the last 10 years by 7 to 12% in the Polar Code area. And the time ships are exposed to hazardous sea ice conditions roughly tripled over the last 10 years. We think there should be a stronger connection between the Polar Code and the Weather and Sea Ice Information Service, one, by broader description of weather hazardous conditions, and second, by the integration of the use of maritime warning systems. Thank you very much.
Great. Thank you, Malte. That was a really good comprehensive overview. Does anybody have any questions? We have 1-2 minutes. Nothing? We have one at the back. Yeah. I think you're going to have to.
Okay, very good. What's your definition of Arctic shipping? Is it just the number of ships in the AIS, or is it a broader outreach to get the numbers that you call Arctic shipping? I chaired the Arctic Marine Shipping Assessment, and we had at the beginning, what do we mean by Arctic shipping, or do we really mean Arctic marine use for, when you collect up all the sectors? It's just a baseline question I have. Thank you.
Yes, so it's a good question. So we only use the AIS data. So what we refer to Arctic shipping is what we get from the AIS data.
Great. Okay, thank you, Malte.
Thank you.
Our next presenter was unable to be here today, and that's Hjalti Reinsson. He's the current program officer for PAIM, or Protection of the Arctic Marine Environment Working Group under the Arctic Council. He's going to be presenting on an overview of Arctic ship traffic data with a video presentation. He recorded it ahead of time.
from ships, traffic in specific areas like the exclusive economic zones, large marine ecosystem, or coast area, and others, and number of ships in Arctic ports. Its goal is to provide reliable data for use. PAIM really wants to provide and promote Arctic research and development by offering this high-quality data for use. PAIM and the Arctic Council use the data from the system to conduct analysis and develop projects that will benefit many different projects across working groups under the realm of the Arctic Council. Each user is designated an access via a username and a password, and they can download the data for their own analysis for their various different projects. And users also can add their own data to the system. Several high-level organizations and entities have access to ASTD, and of course many Arctic government agencies and ministries. The data can be used by the permanent participants and working groups, and then several of these professional institutions have had access, and then many Arctic Council observers, obviously ranging from Korea to WWF. The data comes, as I said earlier, from around 100 satellites from Norway and USA. It collects AIS signals from ships and allows for analysis on detailed information for each individual ships. And the information that we have include the MMSI and IMO number and the name of the ships, the type of ships, their flag, their ice class, their age, their size, including their gross tonnage, the passenger capacity, and then we also perform calculations on the distance they sail in nautical miles. We have the information on the fuel they use, and we make calculations on how much fuel they consume. And we also can count the hours they operate in the Arctic. We also can see and aggregate, calculate the consumption, not only of the fuel, but also on CO2 and other emissions. These calculations are provided by DNV, which we collaborate greatly with within this project. And the system is hosted by the Norwegian Coastal Administration in Norway. Here is the ASTD system, just to show you a bit how it works. I'm now currently looking at the ship tracks of gas tankers in the Arctic. You can see there a slider where I can move around between months and years. Now I'm toggling on to see bulk carriers, zooming in to show the traffic there in this specific area around Russia. Then you can choose an area such as this one, the polar code area. And then you can choose to look at, for example, cruise ships, look at the number of cruise ships for 2 specific months, just for a short comparison. And then in just a matter of seconds, you see these 2 numbers to compare the number of cruise ships in the polar code area. So you can make several different reports. Here we can look at the number of ships going to the port of Akureyri, and there you can see the types of ships coming in and the number of ship type. This data can then furthermore be downloaded, so you have information on each individual ship. For example, there in the polar code area, and then from this Excel sheet that you get when you download the data, you can perform a number of different analysis to whatever you're interested in, and it's quite easy to work with when you have Excel, and some not a whole lot of specific skills are actually needed to make sort of easy analysis. And an example of that is just to show you here number of ships in the Arctic Polar Coast area. These are unique ships, so each ship is only counted once. So you can see there a 10-year trend, the development of ships from 2013 to 2023. There's an increase, and now I just completed to look at the 2023 numbers, where you can see 1,782 ships in the Polar Coast area. You can also look at the distance the ships are sailing. We aggregate this for each individual ship. So the numbers here in this 10-year trend has doubled from 2013 to 2023. You can see the increase there. I've added a linear trend line to this graph, just showing you the distance sailed, highlighting the increase. You can then also look at the types of ships. These are the 1,782 unique ships in 2023 operating in the Arctic Polar Coast area. You can see there that it's dominated by fishing vessels, 723 fishing vessels, and then 181 general cargo ships, and then the list goes on. PAIM has used the data for several reports, including on tourism, underwater noise, and marine litter. But we also have a specific project called Arctic Shipping Status Reports, where we use the data to provide short, factual reports on different topics. We have produced 4 reports to date, and they have been approved by the PAIM working group. They are on the increase of Arctic shipping, heavy fuel oil, shipping in the Northwest Passage, and on flag states of ships, which was just approved in December. We also have a report on the types of ships, hopefully to be published just in the next couple of weeks. And we are producing more of these reports, including on bulk ships in Arctic mines, fishing vessels in the Arctic, black carbon emissions from ships, Arctic marine tourism, underwater noise, more stuff on marine litter, and then we are developing more ideas for the coming reports. Here's just to show you one of the information from the recent report on flag states. As you can see, these reports are sort of graphical and are meant to be easy to understand for people interested in these topics. And here, a simple table identifying the top flag states, actually all of the flag states. Here's the top 20, and you can also see another list there on the right. And of course, all of these reports are available on the PAIM website. Showing here that 312 ships in 2022 were from non-Arctic states, 117 from European nations, for example. This is it for me. I encourage you to email me for any information. I'm happy to provide information and make this presentation available to anyone if they request it. Thank you very much.
Okay, thanks to Hjalti. He's obviously not here, so we won't be asking questions. We're going to move on to Bernhard Schmitz. He is a professional software developer within the Drift and Noise Polar Services, and he's going to be presenting on how much travel time could we save using a navigational assistance system in ice.
Yeah, thank you very much, and welcome to this talk. We were developing service for ice route calculation within the FastCast2 project, and so this service should be based on Earth observation data. And while we are doing this, we ask, is it worth the effort? So how many travel time can we actually save using such a service compared to traveling with optical observations, like if somebody on the ship just looks out of the window, or based on ice radar. Therefore, we did some comparison, which is not based on real ship data, but on some virtual ship tracks, which we simulated, doing some smaller adaptations to the way how our algorithm considers input data. So input data for us is classified Sentinel-1 radar data, which comes as with a resolution of 160 meter and should be able to also consider smaller features in the ice. This data is provided by our project partner, DLR. And yes, we use that data for route calculations. The virtual chip we are using, it needs or has some properties. So for example, we need to assume a speed at which the ship is able to travel through the ice or open water, we are considering these three different types of surface types. So we consider open water, we consider multi-year ice, which is the most expensive type, and we merge all other ice types in a third class. Using the input data and the ship properties, we're using an anytime repairing R-star algorithm for calculating the optimal route. And we optimize for time for now. Later on, we might optimize for fuel or something, but for now, we keep it by the time. So the best route is the fastest route. So now we want to do this comparison. Therefore, we introduce another property for this ship, visual range. So we say for the optimal route, we consider all input data we have, but for some kind of limited routes, we consider data, for example, within the optical range, so 2,000 meters around the ship, or for ice radar, so 7,400 meters around the ship. And this is an example for that. So the easiest route suggestion would be line of sight. Of course, nobody wants to travel like this, and it's the most expensive route, but it's the shortest route. The next solution is for a visual range of 2,000 kilometers, so like when somebody is doing optical observations. And we see that there are already small deviations from the line of sight route. So some situations where the ship was able to use some leads in the ice to avoid traveling that much multi-year ice. And it's already 18% cheaper or faster than traveling along the line of sight. Next solution is for 7,400 meters visual range, and we can see that the ship is able to use even more open water leads and other type ice, but not multi-year ice. And it's 26% faster than line of sight and 10% faster than the optical observations route. And for comparison, this is now the optimal route, which considers all data we have available. And it's, again, 22% faster than the ice radar-based route. But we can see that the travel distance, of course, is a bit larger, as this route decides to travel further into the east and make use of these open water patches. So how did that work? We start at a location which is denoted by this red dot here, and then we say, okay, we let our algorithm consider all nodes or all pixels which are within the visual range, and outside the visual range, we assume multi-year ice. And then our algorithm gives us a solution for this situation. Then we move on and say, okay, now the current position of the ship, again the red dot, is the first position or the first waypoint of the calculated route. And we calculate another route with origin in this point and, of course, our target. And we repeat this multiple times. Now we have another route suggestion for the path ahead. And finally, we end up with, having such a limited visual range route if we just merge all the current positions together. We did this for multiple scenarios. Here on the left side, we see it for a rather homogeneous ice condition, or a less complex ice condition. And on the right side, we see the same for a rather complex ice condition or inhomogeneous ice types. And that is the result. So we see that in general, for increased visual range, the saved travel times, it was possible to save more travel time. And there's a contrast between the homogeneous route, the yellow one, and all the other routes. Therefore, I plotted the mean value for the more complex ice type routes, and we can now see that for the optical-based route, we would save 32% if we would use the optical route instead of this optical observation-based route, or we would save 27% if we would use the optimal route instead of the ice radar-based route. And for the less complex ice types, we are somewhere between 15 and 10%, which we save. So on this slide, we can see some surprising situations where a route calculated for a smaller visual range is cheaper than the route for a larger visual range. I can comment on that by an example. So the red dotted line is the example we had before. So it's for 12-kilometer visual range. And now we start at the same point, but with a 10-kilometer visual range. And we can see that at some point, both solutions agree, because now the 10-kilometer range route figures out, okay, it's maybe better to travel this other ice patch. But then suddenly it decided to use this open water patch in the south. And if we zoom out, we can see that although this solution for a larger visual ice range was faster in this current situation, on the long term it wasn't faster because it didn't see what came beyond. And this, as a result, it had to travel a route which is 2 hours and 34 minutes, takes more time than the 10-kilometer solution. Of course, the price we have to pay is increased travel distance, which we cannot see this graph. And now I run out of time, so no conclusion, but yeah, thank you for your attention.
Thank you, Bernhard. We're going to move straight on, but thank you very much. If you have any questions for Bernhard, please take contact straight afterwards. Now I would like to introduce Qianxian Zhu. There you are. She's a postdoctoral researcher at the Institute for Technology and Safety at the Norwegian Arctic University here in Tromsø. And she's going to be presenting on multi-stage, multi-criteria route planning and optimization for fishing vessels in the Barents Sea. Thank you.
Yes. Hi, good afternoon. I'm Tian Tian. Right now, I'm a postdoc working for the SPRIS project at the UIT. Today, I will talk about multi-objective route planning on the optimization using the combination of graph theory, genetic algorithm, and Pareto optimality for fishing vessels in the Arctic. The project I work for is called SPRICE. Or SPRICE, they call it SPRICE. In Norway, they call it SPRICE. It implies multidisciplinary approach for spray icing, modeling, and decision support in the Norwegian maritime sector. I think the first presenter talked a bit about spraying icing already, and the picture is how spraying icing looked like on a ship. And Masoud Nadari is the project manager. This project is mainly funded by Norwegian Research Council, and we have partners including Sjø UiT and the SINTEF and the Hermes and the Norwegian Coast Administration and the Norwegian Meteorological Institute and a fishing company called Hermes and a fishing farm called the Granton Lux. Now I think here is, you have seen a lot of these maps already in the previous presentations. Here is just a plot of fishing vessels of 1 month using the AIS data from ATASD, the second presenter talked about. So we use their data. And this just shows like how busy it is in the Arctic and how many fishing vessels there for 1 month. And we look at I tried to check the patterns of fishing routes, but actually I realized that this is just one example of how the routes look like. After I checked the thousands of routes, I realized actually never two routes look similar. Each route is very unique, and therefore it means that actually there are a lot of dynamics and uncertainties involved in the fishing route, which also implies that actually planning and optimization are needed more frequently than other type of ships. In our case, then we're trying to do routing for fishing vessels, which involves solving the problem of what route a fishing boat should follow. Actually, the previous presenter already talked about route optimization, but here is a bit different. And then we also try to optimize the speed for the fishing boat passing through different route segments, and the time that the boat should stay at a different fishing ground. Here, when we look at how a fishing trip looks like, we can simplify it into a series of hierarchical and sequential decisions, from tactical decisions involving determining what regions should I go for fishing in general, and what seasons and the targeted species and the quota to purchase, and to the end, to the to the exact fishing spot when I drop the fishing gear. And in our work, we focus on the route decisions and the next action determination, which means that we try to get optimal routes, but we don't try to follow them strictly from the beginning to the end. Instead, we just determine the next place to go and the speed and duration and so on, and to encounter the dynamics and uncertainties, and we re-optimize again to get the next location. But I think the previous presenter talked a bit about this as well. Actually, it doesn't necessarily give us the optimal out of optimal eventually, because there's so many uncertainties and dynamics we cannot see in the beginning. But I think this logic is kind of in the right track. And for the proposed algorithm for routing, we use graph theory to represent all possible routes, and then we use genetic algorithm and the parallel optimality to determine the optimal route according to our objectives and the current status and the fishing, the vessel conditions and so on. After we get the set of optimal routes, then we try to select the next action to conduct, including the location, speed, and the duration and so on. And then we re-optimize again. Here is this table just summarizes the algorithms, and here is an example of how graph theory look like when we use it to represent a route, a route network or like route candidate. And when we try to express a route, we express a route as a combination of a sequence of locations to go and the sequence of speed and sequence of duration at each stop. In this way, we get like optimize the spatial and the temporal dimensions in a route. Because when we look at the weather forecast and so on, it's really like temporal and time dependent. So therefore, it is quite important to involve not only the geographic locations, but also the time dimension. Here is, because when we talk about optimization, it is very important like to how we link the route to our objectives, such as fuel consumption, and safety, and the time, and the catch, and all this. Then here we call it like objective modeling. We have to establish an objective function between the route and our objectives. And then in this objective function, we have to link the weather condition and the ship condition and so on. And also, very important, the fishing stock, because the important is to catch fish, yeah. And I will not go through this because this is more like the method part. Yeah. And here, in end, I just want to say like how we do, what we do in a routing. If we have a set of possible locations to go, fishing ground to go, and factories to deliver the fish, and the ports and so on, and we try to establish our objectives and the objective function, and then from the initial place, we get a set of optimal routes, and like in this case, we get 3, and then we determine from these 3 optimal routes, we select the next place, and then after we reach the next place, and we after getting catch, we re-optimize and determine, we get a new route and determine the next location again in case the catch is not satisfactory. And here the whole route is finished. For further work, because it's just ongoing work, we will focus on like objective modeling, like how we model the fuel consumption and the route in relation with the route, and how we model the risk or the safety in relation with route, and also the cost. But also we would like to have some real fishing vessels as examples to test and try out our algorithms. So if the audience who you are on or working for a fishing company, feel free to contact me if you are willing to try out and contribute to our algorithm development. And also we want to continue developing the routing platform, which includes the data, AIS data, and historical weather data, and hazard data that the first presenter has talked about, and also the fishing stock distribution data, and also potentially we can use those data to derive our preference towards certain objectives, because it is very difficult to say for different fishing skippers, they may value safety than catch. For others, they may value catch than safety. So so there is some compromise, and from their choice of route, we can actually see how they prefer, what they prefer, and we would like to include that in our fishing route optimization as well. In this way, the skippers and the ship owners, they can actually customize their route according to their objectives and the fishing, that there was the conditions and so on. And together, we hope that this can contribute to develop a more sustainable and more efficient and greener and safer Arctic. Yeah, thanks. I hope my presentation is interesting. That's all, yes.
It was interesting.
Thanks.
We don't have time for questions, but I do encourage you, if you are in the fishing industry or one of the end users, to get in contact with.
Yes,
Tian
please.
Tian.
Yes.
It's really, it's really important for algorithm development. Our next speaker is Andrew Fleming. He's the head of mapping and GIS at the British Antarctic Survey and leader of the Horizon 2020 Arctic Passion Project Pilot Service 6 for improving safety in the polar seas, which is what he'll be presenting on today. Thanks, Andrew.
Thank you very much, and good afternoon. Thank you very much for the opportunity of presenting this. I'm going to concentrate on one particular aspect of the Arctic Passion Project, but I would encourage you to go and have a look at the website, easily found by Googling, and the address is at the end, but this is a very wide-ranging EU project aiming at developing a comprehensive user-led observation system for the Arctic. As part of that, there are a number of so-called pilot services concentrating on testing the delivery of real information and trying to improve that to make sure that there's a real use of the information, the observing system that's being developed. This presentation is concentrating on one of those, which focuses on shipping, luckily for this session, and I'm going to be presenting some initial results from that and our approach to it. I am presenting on behalf of several colleagues, so acknowledgements to them, especially colleagues from University of Ottawa and DMI who have helped out with this. So for context, we're talking about understanding, better quantifying the level of risk that ships are exposed to while traveling through and around ice. This is relevant in terms of, well, a number of timescales, really providing better quantification of risk, both on a long time series, if you're trying to decide what polar class vessel you're going to build, on a seasonal time scale if you're trying to plan your activities as an organization or a ship operator, and then also on tactical decisions in terms of whether you're making decisions on an hour-to-hour or longer term basis. But that information about what are the operating limits of my vessel and what does that mean for the vessel operating in the ice conditions that it's currently exposed to. So that's the intention. The basis of it is using the Polaris risk assessment system. So I realize there are some overlaps here with some of the first presenters' work. Maybe the difference here is that this is the approach we've used in terms of Polaris, more of which later, but it is very much part of the risk assessment system that was set out whenever the IMO Polar Code came into effect. There are 2 or 3 different parts of this pilot service. The bits I'm going to concentrate on are 1, the historical analysis, and 3, a little bit on the forecasting work that's gone on as well. But please feel free to ask me later on about any other aspect that you want to. I should just point out as well that we're very much trying to co-design this and make sure we're getting input from all involved. So we've, as you've seen to start off with, got quite a range of people involved, but we're also consulting with a wide range of other experts in terms of the ice services, ship operators, insurers, etc., as we go through. So for those of you not familiar with Polaris, it's I'll not read out the acronym there, but effectively it's a system for allowing a user to determine the limits of operation of their vessel in ice conditions. I think slightly differently, it takes into account key things like the current ice conditions, and for that you need to know factors like what type of ice, stage of development, effectively, and then also the concentration of the ice, how much of it there is. But it also takes into account the actual polar class of the vessel that's determining the risk, so it's not separate from that. You can get the information about the sea ice information, the sea ice conditions from a number of sources. Simply put, you can look out the bridge window and make an assessment yourself, or you can use the ice charts, which provide, and nearly all ice charts provide information not only on the concentration of sea ice, but also on the type or the stage of development of sea ice. So from that, a relatively simple calculation results in a traffic light type calculation where a negative RIO score, this is the RIO, I'll refer to that again as the risk index outcome. If it's positive or 0 or positive, you're good to go. If it's negative down to -10, then there are certain limitations, but less than -10, and effectively you're outside the limits of operation of your vessel. So one thing that we have discovered through this and other work is that I think it's widely accepted at the moment anyway, that the use of Polaris, certainly on board vessels, the uptake is relatively low. And so one of the things we're trying to understand from this is why that is, what improvements need to be made, and then contribute back to any revision of the system. If you're interested in the current limitations of the Polaris system and work that's been done under the banner of the International Ice Charting Working Group, there is a task team which I've referenced at the bottom there, which has gone into this in some significant detail. It also includes a number of case studies for I think it's about 5 or 6 different case studies looking at feedback from particular vessels which calculated Polaris, assessed it alongside their the conditions they were operating in, and then provided feedback, which has been really informative. Like a lot of others, we are also using the PAIM ASTD database to provide the information of where the ships are, what time of year they're operating, and trends in the volume and type of ships operating in the Arctic. These are 2 graphics, 2013 on the left, 2019 on the right. There, if you look closely, there is clearly a change in the volume of traffic. But the other aspect that we need from this is the polar class of all of the vessels. I know there is some information in polar class or ice classification of vessels within ASTD, but we've had to do quite a significant amount of work to get that unified and complete so that we have a PC rating for all vessels necessary for calculating the RIO, the risk outcome for each vessel. So what we've done is taken a number of years' worth of historic ice charts from the US National Ice Center. They usefully cover the entire Arctic and also include both the sea ice concentration and the stage of development information that we need. We have then matched those charts up with the locations of each vessel. We've got a mean daily location, and if we've got a daily location that matches within the 4 days preceding the issue of the ice chart, then we consider to get a valid record of a ship at a location with information from which we can calculate a risk outcome. So obviously that filters out quite a lot of data because we're cutting it down to those where there's a within 4 days preceding an ice chart issue, and ice charts are only issued every week or 2 weeks in some cases. But the observations for the ice charts are generally within those, the observations used to construct the ice chart are generally within the few days beforehand. So it's not a perfect solution, we're trying to revise that, but for the time being, that's the approach that's been used. So we've got data from 2016 to 2021, and for each vessel record, we have calculated we've calculated the Polaris charts for all years, all weeks, and then matched those up with the ship locations to give us information on what risk value the ship is using at any particular point. So essentially with them, we're analyzing that data to give us a better understanding of how Polaris is working. I mean, broadly, you could look at it and go, is Polaris working? Assuming it is, but is any change because ships are actually taking more or less risk? Or is there something underlying the ice information we have that's not of sufficient accuracy or resolution that limits its use, or is there something else about the methodology that isn't quite working? For example, you have to choose risk values depending on whether you think you're in summer conditions or winter conditions, and that choice is a bit arbitrary. Sorry, if I go back one. So this is, on the right-hand side, is just a really simple output then of all of the ship locations. In blue, you can see most of them are in that normal operation. Sorry, it should have been colored green. But then more widely, you can see that there are various hotspots around here, Hudson Strait, Pond Inlet, Eclipse, etc., where there are clearly hotspots of where there's higher risk activity taking place. But then you can look at this and start analyzing the results in a little bit more detail. For instance, across the top, then we have, for these ship records, then what's the pattern? And whilst again we see a gentle increase in the number of ship records, i.e. the correlate with the amount of ship traffic, the level of operations or records where it's higher risk, either elevated risk, that middle amber, or the red, extreme risk is relatively flat. And then we can break it down by year and equally see trends such as most of the higher risk operations tend to happen in the early part of the season from February through to June. I should point out, please ignore the 2018. There's certainly some anomaly with this. And I should have pointed out as well that these results are only from the Canadian EEZ, or the Nordreg zone. So I'm running out of time slightly, so I'll rush through these last couple of slides. But again, breaking these numbers down, not only by the records, but then also by unique ship to get an idea of where some of these trends are. And the anomalies, again, in 2018 is something to do with apparent, but probably unreal amount of extra shipping going on. The next step with this then is to expand this beyond the Nordreg zone and do it for all of the other regions of the Arctic. And within the rest of this year, now that we have the data compiled, we'll have results for the whole area. One last comment then, moving very quickly to the forecasting element. So some of the feedback we've got from ship operators that have been working with us is that the forecasting element of this is highly useful. So there is an initiative. We now have operational forecast being produced based on the ECMWF model, which includes sea ice concentration, sea ice thickness. The stage of development only uses a proxy for thickness anyway, and from that we can again calculate forecasts out to about 40 days, but at a very coarse 25-kilometer resolution. So clearly need to use much higher resolutions models if we can. Next step as well, we're hoping to run some trials in the coming year with these partners, both the maritime training academies, who are making great use of it, and then some ships operating in the Arctic. I'll stop there. Thank you very much.
Thanks, Andrew. I think I was a bit optimistic with time for questions at the end, but if you want to get in contact with Andrew, he's there. Now I'd like to welcome Abby Tingstad. She's a research professor at the Center for Arctic Study and Policy at the US Coast Guard Academy, and today she's going to be presenting on the potential priorities for data needs to support the future Arctic blue economy. Thanks, Abby.
Thank you. All right. Good afternoon. I'd like to thank Arctic Frontiers and our session organizers here for hosting this session, and I suppose I also need to thank Scandinavian Airlines for taking one more standby passenger this morning so I could be here with you in person. I'm going to actually pivot to some social science research that we've been doing, which really speaks to a concept that we here at Arctic Frontiers understand, but not necessarily appreciated by the broader policy community, namely that there are in fact many Arctics. And I think in the big picture session earlier today, they really spoke to the importance of this concept of many Arctics for policy. If we think about the action-reaction calculus, it really depends on where you are in the Arctic and what factors you're looking at. So, and this in turn then also impacts our data needs. And as I mentioned, I'll be speaking to some social science research. There's some other aspects of the project that I'm not presenting today that actually does look at the physical science as well. But since we've already heard some excellent presentations on shipping and similar research, I'm going to focus on the social science aspects here. Okay, so I just mentioned that depending on where we are in the Arctic, your action-reaction calculus may be very different. Also depends on what factors we might be considering, and you can see some example factors here. We have a number of local characteristics in different Arctic communities and Arctic areas that characterize the region, might impact how change is occurring there. now in 2050, it definitely has an impact on the trajectory in which different parts of the Arctic are moving. But we also have some global factors, such as demand for resources, among other things, that really impact then the interest globally in the Arctic as well. And of course, then we have some overlapping factors, such as climate change, which impacts both the local characteristics of different places in the Arctic, making them very different from each other, as well as having a global perspective as well. So the research that I've been involved with is part of a large multi-institution project called Converging Pressures on Arctic Development. And this does not necessarily have a distinct maritime or marine use focus, though that is, of course, an important aspect of the work. So I'll be speaking more generally about Arctic change, but I don't think it'll be difficult to see the connections to the maritime environment and issues of safety, issues of planning for this environment, and the issues of developing data sets and understandings in order to continue to develop policies that make sense for the region as it continues to change. So as I mentioned, one of the major findings of this research to date, which I'm not sure is a finding so much as a demonstration of something, as I mentioned, that we know already, is that there are indeed many different Arctics, and we can characterize some of these trajectories through the research that we've done. I'll briefly go over the methods. Happy to talk with you later if anyone is interested in learning more about the Delphi technique. In brief, it is a consensus building approach that uses anonymous surveys across a wide range of experts in different rounds. So you do a round one, then you have some discussion in between, and you see if your experts then convince each other so as to potentially build consensus in a later survey. I'll bring your attention to the fact that this work was done, this part of the work at least was done in 2021, and I know we've had some really substantially impactful events since then, but in some cases we don't think that the results of the research would have changed that much. I should also let you know that we, for the purposes of this work, we divided the Arctic into 4 subregions to explore some of that variability. This was done primarily based on geographical and cultural connections, as well as some connections between economic sectors. This is something that one could divide the Arctic into many ways and never get it perfectly correct, of course, from everyone's perspective, but this is one way of doing it, and it facilitated the look at variability across the region that we wanted to see. So on these surveys that we delivered to the experts, we had a variety of outcomes that we asked them to look at. We looked at several economic sectors in addition to selected social factors, and we asked them questions, for region Barents. How likely is it that some particular outcome could occur by 2050? And the purpose, again, of really doing this was to see how different do these experts see different parts of the Arctic now and as they're changing through 2050. So I'll just show you some examples of the results here. Here is one of the outcomes that we asked our experts to look at, namely, will Indigenous self-determination expand in each of these 4 subregions? And just to orient you as to what you're seeing on these charts here, for our expert surveys, we had a round 1 and then a round 3 where they did the survey. Round 2 in between was a discussion period. And you can see here that there is some changes between the number of responses in each category between round 1 and round 3. We asked our experts to rate the outcome plausibility on a 5-point scale, 1 being not likely at all and 5 being almost certain. The 3 was representing neither likely nor unlikely, kind of a neutral response. And one thing that you see here, for example, is that there was some optimism about Indigenous self-determination expanding in these different areas. Definitely, though, especially in the comments in round 2, we saw a lot of concern about the Indigenous situations in Russia, which is one of the reasons why, for example, Central Siberia has a more, if you will, more negative outlook on that particular outcome. Just to give you a flavor for some of the other outcomes that we looked at, we looked at whether more food would be produced. Some interesting discussion items here. Certainly some focus on the ocean and fisheries, but a lot of comments on agriculture. So as an example, one of the reasons why the Nunavut, Greenland region had a big bump up in fours for the third round was because there's a lot of discussion about the potential for growing agriculture in Greenland, among other things. So we also looked at whether hydrocarbon extraction would increase. This is one where I'm not sure if the responses would have changed if we did this again now, because obviously post-Ukraine, there might be some different perspectives. We heard about some of those, for example, in Norway at the big picture session earlier. We also looked at the issue of whether mining will grow, and one interesting thing on this particular chart is you can see a lot of disagreement when it comes, again, to the Nunavut Greenland subregion that we looked at, and that was largely reflecting a lot of the internal debate within Greenland about the future of the mining sector there. Probably the most consistent outcome that our experts thought would rise or increase by 2050 was that of tourism in the Arctic. And I think that is really relevant to this session because it is still an emerging area, something that's very important to consider from a safety perspective, from an environmental integrity perspective, among other things. We also asked the question about military operations. This is another one that, who knows, may have had a slightly different response, but there was already some consensus that there would be a growth of military operations in the Arctic region for the most part, even in 2021. We did some analysis on the written comments that our experts provided, basically looking at the frequency of words that were used in the discussion. So I'll just give you a sense for what was discussed in the Barents region here through these word clouds. Here's for the Bering-Beaufort region, Central Siberia, and then finally Nunavut and Greenland. If we look at some of the similarities across the top 10 terms mentioned in each of those areas of discussion, we do see some similarities, but we also see a lot of differences. One of the things that concerns me actually is that there was much more mention and discussion of land as opposed to ocean or coast, which I think is one good motivation for having these series of sessions, because obviously we need to be having some more conversations about the ocean. Okay, I will just conclude here by saying that developing common priorities for marine use, activities management, and governance could become even more difficult as the different regions of the Arctic might be on diverging trajectories in the future. So that kind of makes our work in policy and science even more difficult, if you will. There are some common areas of interest that we saw: climate, demographic, technological, and other sector-specific data being common, which is good. But additional prospects are needed for consolidating data and knowledge curation, including traditional knowledge. And I'll end with that. Thank you.
Thank you so much, Abby. You can stay up here. We have about 10, maybe 15 minutes left. I'm going to ask the presenters that wish to come up to the stage, and we're going to have a quick panel discussion. So if you'd like to take a seat.
Yep.
Andrew, Abby, Chan, and Malta. Yeah. Hjalti's not here today. So the question I'm going to propose, we all know that, I think, listening to all of this, that climate is very important, climate change is a big topic, and climate data is important, and that we're collecting climate data. But one thing I want to put towards the panel, something I've seen, is that, we're looking at these short-term forecasts, we're looking at this, everything seems to be very sort of short-term tactical. So I wrote a question that, do you still consider it a valid approach to use current climatology to shape Arctic policy? I know it's a difficult question. And then, of course, if not, what's your suggestion to improve that? Who would like to begin? Go ahead.
Well, I could say a few words. I think it's a question that we're definitely grappling with now, but I think that's starting to change. I think we're seeing more examples through efforts such as these to actually look at future projections in order to shape Arctic policy. But one of the real challenges is that a lot of policy is driven on very short time cycles, whereas sort of the broader strategic perspective is really looking out into the future over many decades, but it's really hard to connect decisions of today with those of the broader future. And one example that we're facing in the United States right now is been talking for many years about how many icebreaking vessels that the US should be operating. And this is obviously a very expensive and important strategic question. And one of the challenges I think that's being faced is kind of this cycle of, well, we need to decide our budget over the next year or next 5 years versus US operating in the Arctic using these vessels. We could be looking at many decades hence.
Great response, Malta.
Yeah, so to add on this, I think it also depends what's the purpose you are asking for. So if you're really interested in an average over a certain time frame in the past, then I guess using a climatology is the right thing. But if you use it for, let's say, route planning, like the example I showed, then climatology has certain disadvantages that you kind of average out the extremes, and so you would have to give the users this additional information, and that's something we also had in discussions with users, that they were certainly interested in using climatologies for decision making, but then they asked us also for giving them the most extreme conditions which happened, for example, in the last 20 years. So just that they can put this kind of average into perspective. So I think then you can still use a climatology, but what I showed today is also that, I mean, we have very good forecasting systems and they are steadily evolving, and we are also improving on our methods to calibrate these forecasts for end users. So in that respect, I think we should move on, like for this type of questions, we should move on and actually give the users also forecast information.
Yeah. Andrew?
Very, very quickly, yeah, in terms of sea ice climatologies, I think I've certainly noticed requests for shorter time periods because of an awareness of things have changed fairly rapidly recently. Definitely the case in the Antarctic, which my backyard last 5 years are completely different from preceding, so that's changed. But I referred in my presentation to the International Ice Charting Working Group, which is the collection of the ice centres, and the working forum for the ice centres, and they have active work at the moment, looking at a task team, looking at how to standardise and harmonise the sea ice climatologies to make sure that they are fit for purpose, and part of that is the timeline that they'll consider.
Yeah. You have any comments, Jantan?
I totally agree with what they have said. I think both when we talk about the climate, it's more like long term, and then we talk about weather, that's more like short term, what happened today or tomorrow. But sure, like when I think about it, I take bus, so I walk to the conference center, I look at the weather forecast, I don't look at the climate, right? It's like very long term. But then when you talk about the maritime policy, it's about what you are considering. What kind of policy you want to design and how long term you want to consider. Then it determines like whether you use climate or use weather. But I think it's true that when we think about extreme conditions, like what happened today is not so extreme, okay. In terms of the weather, it's not so extreme today. But weather forecast or what we have experienced, like the weather forecast today is actually provide us the extremes. So we should consider this, yes, in the long term as well. But I think in climate, they also consider extremes, right? Like they do average out, but they also consider what is the extreme case and what is the worst scenario and so on. I think, yeah, but then, yeah, I think that is included. But still, my impression is like what kind of decisions you are looking at is the most important factor to determine whether you use short term or like long term. But in another thing is like what we are doing today actually determines what will happen in the future. That is what you address, right? So it's, that part is very difficult. I cannot figure this out. But I think it's like we used to, maybe many of you have heard this Markov decision process. It's like we want, yes, it is sequential, but we, yeah, it's, how should I say? But in the future, like even though we have the historical data, but there are a lot of things we cannot foresee right now. So we may have to be inclusive and keep the options open. Yes, keep the options open. So in case something happens in the future we didn't foresee, but we still have something. We still get prepared for these kind of things we didn't foresee in the past. Yeah. I think that is called resilience. Yeah, maybe yes. That is something we can look into.
Yeah, that's a great response. I think it's something we do talk about. Now we're seeing all of these more extreme events as we're coming up. Climate change is causing all of these different things. Maybe it's now the time to think of, instead of the traditional climatology, maybe we should be looking at smaller base periods or these smaller time periods in order to look at these more extreme events that are happening in order to take those into account. I'm being pushed for time. Thank you to all our speakers. If you have any questions, I'm sure the speakers will be hanging around for a little bit. Please just ask them questions, go for coffee, etc. I would also like to say, this is a perfect opportunity at Arctic Frontiers. It's not very often we actually get policy, research, operations, and end users all into the same room. So this is a really good opportunity for us to connect and to network with each other. So thank you for joining, and hopefully see you tomorrow at part 2.
Thanks.